Hello everybody and welcome to another college algebra lesson. In this video I will be going over more exponential and log equations. We will start out with this new idea from the last video anyway, where we will have log equations where all terms are logs. We will go back and review what log equations look like and how to solve them when not all terms are logs. We will also go back and review exponential equations and how to solve those, two different ways. Then we will jump over into the different categories of equations, if you will, and we'll just play a little matching game, like how do you know which way to solve this equation? Is it logarithmic? Is it exponential? That'll be helpful for you if you are in any sort of college algebra course. We'll take a look at some more money examples. This time we will be solving for like an interest rate or how long you need money to sit to make a certain amount, so on. And the last thing is we will talk about the domain of functions. So we're going to take a look at all the different types of functions and their domains. Let's get to it. So, how do you solve log equations when all the terms are logs? The first thing we need to do, and this will make more sense in a little bit, is we just need to make sure that there's only one log on each side of the equation. The second thing you do is, since they will have the same base, and we're talking about they being the logs, since they will have the same base, we are able to set the arguments equal to each other. From there, we can solve and check our answer. So just diving right into example 1, you can see that there are two logs, one on each side of the equation. And again, this equation only has two terms. There's one term here, it's a log term. There's another term here, it's a log term. Once you have one log on each side of the equation and no other terms, then you can just set the insides equal to each other. So 3x plus 4 and 5x. And then you can solve for x by subtracting 3x from both sides. So that's 4 equals 2x. You can divide both sides by 2, and you'll get x equals 2. But like we did with the other log equations that you've learned, you have to check your answer. And again, it's as simple as taking your answer, x equals 2, and substituting it into each argument that has a variable. So here I see 3x plus 4. All right, let's take 2. We can substitute it in here. 3 times 2 is 6. 6 plus 4 is 10. That's a positive number. So that means this answer is good for this log, but we have to check all the logs. So we also have to take 2 and substitute it in for this x. 5 times 2 is 10. That's a positive number. Again, it has to be that the argument is positive. It's not even allowed to equal 0. So we're good to go here. Let's take a look at some more examples. On this slide, two more examples, pretty straightforward. We have the natural log of x squared equal to the natural log of negative 4x plus 5. These are all log terms. And again, this will make more sense when we get into examples that don't have all log terms. But for right now, this term is a natural log, this term is a natural log, the bases are the same, we have one log on each side, which means we can set each argument equal to each other. So x squared equals negative 4x plus 5. So this one is a little bit different because when we set the arguments equal to each other, we ended up with a quadratic equation. Last slide, it was linear. Linear is pretty simple, but this one, we're probably going to have to get that equal 0 and see what happens here. So we have x squared let's add 4x to both sides and subtract 5 from both sides to get this equation. And then always, when you have a quadratic equation, you want to see if it'll factor first, and this one does. So we have x plus 5 and x minus 1. These are the two linear factors. From here, we can set each factor equal to 0 and solve for x and get x equals -5 and x equals +1. Now we got two answers. We have to check both answers to see if they both work. So let's start with 1. 1 is a nice, easy, positive number to work with. So let's see, 1. If I square 1, I get 1. That's a positive argument here on the left side. If I take 1 and substitute it in here, I get -4 times 1 is -4. -4 plus 5 is also 1. So the argument here becomes 1 if I substitute 1 into it, a positive number. So yeah, I know this one is good. For this next one, -5, the -5 we're going to substitute into x squared, or in for x, we're going to square it. -5 squared is 25. That's a positive number. So -5 works in this log, but what about this one? -4 times -5 is 20. 20 plus 5 is 25, also a positive number. So I want to make a note here. First, x equals -5 is a good answer. It's okay to have a negative answer, as long as it makes all of the arguments in the original equation positive. So again, this -5, when you square it here, becomes a positive 25. When you substitute -5 in here, your argument becomes positive 25. So it is okay for that to happen. You are allowed to have negative answers as long as they work in the original logs. All right, example 3. Same idea. We have one log. All the terms are logs, and we have one log on each side, which means we can go ahead and set all of the arguments equal to each other. So x squared minus 9 equals -8x. We can add 8x to both sides to get x squared plus 8x minus 9 equals 0. We can factor this. What is this? X plus 9 times x minus 1 equals 0. And get x equals -9 and x equals 1. All right, so here we go. We got to check. The solving part, guys, the solving part here is not that bad. It's the checking part that most students fumble up. So let's see how this works. Let's start with 1. So I'm going to take 1, and I'm going to substitute it into the first x I see, which is this side. 1 squared is 1. 1 minus 9 is -8. Ooh, once you find a log that does not work, that does not give you a positive argument, that answer is no good. It can't be good. So it's only, even though we only checked one log here, we know 1 cannot be the answer because we got a negative argument. Okay, let's check -9. -9, if I substitute it in here, -9 squared is 81. 81 minus 9 is a positive 72. If I take -9 and substitute it in here, I have -8 times -9, which is a positive 72. Yeah, that answer is good. So in this weird twist of events, we have a negative answer that's good and a positive answer that isn't. So it's not about the sign of the answer you get. It's all about the sign of the argument. All right, another example. This one is a favorite because we have fractions. Yes. Okay, so with this then, we can notice that each term here is a log term. There we go. And we have one log on the left and one log on the right, which means we can go ahead and set these arguments equal to each other. So we'll have 3x over x minus 1 equal to 6. And yeah, this is a rational equation, and this is part of what I love about log equations, is that it has the ability to bring back so many types of equations that we've already looked at throughout college algebra or algebra 2 or whatever course it is you're taking, including linear, quadratic, rational. Heck, we could even bring back cubic and square root equations if we wanted to. We could do cube root equations. We can do anything. I limit it to quadratic, linear, and rational, just to really hone in on those skills, because those are going to be super important moving forward in your math career. So anyway, to review, what you want to do is find an LCD here. Luckily, there's only one denominator. It is x minus 1. So we will multiply all terms by x minus 1. There we go. And this side will reduce, and we'll be left with 3x equals 6 times x minus 1. We can distribute that out. Get 3x equals, what do we get? 6x minus 6. We can then, why don't we subtract 6x from both sides? Get negative 3x equals negative 6, right? The only thing that canceled over here were the 6x's. This minus 6 is still minus 6. We can divide by negative 3. We can get x equals 2. Ooh, baby, is that a good answer? Let's see. Well, this also brings up another really good point. We have to substitute 2 into our logs, our original equation. There are no x's here in this argument, so I don't have to worry about that side. The only thing I have to worry about is this log, because this is the only log with an x in the argument. So here, 2, substituted in the top. 3 times 2 is 6 in the top. Substitute 2 in the bottom. 2 minus 1 is 1 in the bottom. 6 over 1 is positive 6. Yeah, this is a good answer. Let's circle it. These last 4 examples have been very, very nicely set up for you. And when I say that, I mean you've only had one log on the left and one log on the right. You haven't had to do any extra math to get there. I want to move to the next slide and give you a big, big warning. Big warning here. Huge warning. There are 4 stars. 1, 2, 3, 4. Like, that's how big of a warning it is. Big red lettering. You must always be on the lookout in log equations for logs that can be condensed. If you go back to the solving process, the first step is to make sure you only have one log on each side of the equation. Of course, that's after you check to see if all the terms are log terms. But we can only proceed if you have one log on each side of the equation. So, I mean, you can see here, you must condense before you can solve. You must condense before you can solve. If you notice that you have more than one log on the same side of the equation, you must condense okay, sorry, got stuck in a loop. Let's take a look at how to solve log equations like for real. This process on this slide should take care of everything from here on out, no matter what type of log equation you encounter. The first thing you need to do is determine whether all terms are log terms or not, right? I mean, you'll see as we get through some examples here soon. But if all of the terms are log terms in an example or in an exercise, what you need to do is condense logs as needed to get one log on each side of the equation. So I made this process a few slides ago, but I'm just rewording it a little bit. Once you have one log on each side, you can set the arguments equal to each other. You solve and check from there. Now, I haven't done any examples like this where not all of the terms are log terms in this video, but you have seen some examples of that in previous videos. So we want to get if they're not all log terms, you want to get all the log terms on one side and all other terms on the other. Condense the logs if you need to. Rewrite in exponential form, and then you can solve and check. So let's take a look at how these processes work in action with some real life examples. All right, example 1. Here you can see we have all terms are logs. Here's one term. Here's another term. Here's a third term. So I have 3 terms in this equation. All of them are logs. What that means then is we have to condense. We don't only have one log on the left side. I need to rewrite this left side so that I will only have one log. That being said, we have to remember that if a log is being subtracted, this argument will go in the denominator. So let's just take a look at condensing really quick. This would be log of 3x over x minus 1. So there is the condensing of that. And on the left side, or sorry, the right side, we still have log of 6. Now this was more to show you, to remind you how to condense something, because if you'll notice this equation I solved a couple slides ago. This was example 4, right before the big warning. So we already know that the answer should be 2. But more or less just to remind you, hey, how do you use that quotient rule for logs? How do you condense when there's a subtraction? Okay, that being done and out of the way, here we have equation or example 2. Log of x plus log of x minus 5 equals log of 14. So again, you can see we have 1, 2, 3 log terms. They are all log terms. So what we need to do is condense where we can. So on the right side, there's only one log. So we can't condense anything over there. But on the left side, we have 2 logs. We have log of x plus log of x minus 5. So with that, we can use the product rule to show that the left side will end up being log of x times x minus 5 equals log of 14. Now look at this. We only have one log on the left-hand side, which allows us to set the arguments equal to each other. So we will have x times x minus 5 equal to 14. And we can distribute the x, and at the same time, I'm going to subtract 14 from both sides. So that'll leave me with x squared minus 5x minus 14 equals 0. And yes, we got something that's quadratic, so we factor x minus 7 times x plus 2 equals 0. And from there, we know that x equals 7 and x equals negative 2. All right, check time. So again, we don't have to worry about checking this log. This log is log of 14. There are no x's in this argument, so we don't have to worry about checking that one. But we have to go back, and it has to be the original equation. We have to check the very original equation. You can't check any condensed part of this equation. At this point, this has become no good for check. So we have to go back to the original. Let's just take a look here. I want to start here with negative 2. If I substitute negative 2 in for x here, I will have the log of negative 2. Oh, the log of a negative argument. This answer, right off the bat, no good. Can't be used. You also can see it maybe a little bit better if you substitute negative 2 here. Negative 2 minus 5 more is negative 7, and that's definitely the log of a negative number. You can't compute that. Nobody can compute that. So what we can do is we can check 7. If I substitute 7 in for this x, I have the log of a positive number. Check, that's a positive argument, it's 7. If I take 7 and substitute it here, I have 7 minus 5 is 2. That's the log of a positive argument. Yeah, 7 totally works here. All right, let's look at some more examples. All right, next example, example 3 here. We have log base 2 of 4 and log base 2 of x minus 7, and they're being subtracted, and 1. All right, so let's do this. We've got this, we've got this. Those are both log terms, but this is not. So we would have to use the blue method from a few slides ago, being not all terms are logs solving method. Here's how that works. We have to make sure all of the log terms are on one side of the equation. Check. The 2 log terms that we have are on the left side of the equation. And any other term has to be on the other side of the equation. Check. This is not a log term. It's on the other side of the equation. We're good. Next, we have to condense. So if I condense these 2 logs, we will use the quotient rule because there's a subtraction here. And that will be log base 2 of 4 over x plus 7. Cool, so that's the condensing of this side, and this will still equal 1. All right, so we determined that not all the terms are logs. We were able to get all of the log terms on one side and all of the non-log terms on the other. We condensed. Now we have to rewrite this in exponential form. That's the only other thing we can do. So we take the base, we raise it to the exponent. Remember, a log is always equal to an exponent, so 2 to the first power, and that will be equal to the argument, 4 over x plus 7. From there, we just go through and solve it, right? This is that LCD thing. We're going to multiply this by x plus 7. Also, 2 to the first power is just 2. So we can multiply this by x plus 7. That's gone and gone. So on the left side, we will have, if you distribute, 2x plus 14 equals 4. We can subtract 14 from both sides. That'll give us 2x equals negative 10. And then we can divide by 2. Dividing by 2 would give us x equals negative 5. All right, so here is a possible answer. We don't know if it works until we put it in our arguments. So we don't even have to worry about the right side of the equation, the entire right side of the equation. Gone, we don't have to worry about it. We don't even have to worry about this log. There are no x's in the argument. The only log we have to worry about is this one. All right, take negative 5, substitute it in for x. Negative 5 plus 7 is a positive 2. So the argument here, when x equals negative 5, is a positive number. Yep, that works. This is a good answer. Negative 5 is the answer. The point for this exercise, again, is for you to see what do you have to do when not all of the terms are logs, right? We have one term that's not a log. That requires us to rewrite in exponential form. Here we go again, another log equation. So you out there, figure it out. Are all of the terms logs? If so, follow that solving process. Are all of the terms not logs? Is there a term here that isn't a log term? If so, follow that process. Go through, do your condensing if you need to, solve, check your answer, set the arguments equal to each other, whatever it is that you need to do, do it. I'm going to slowly release steps through this video, starting in about 5 seconds. And there you have it. X equals 4. And yes, x equals 4 is a good answer. If you take this answer 4, substitute it in for x, 4 plus 10 is 14. That's a positive number inside the argument. 4 minus 2 is 2. That's another positive number inside the argument. Next example. Here we go, example 5. We have log base pi. Ew, what is this pi doing here? All right, log base pi of x plus 2 plus log base pi of x minus 2 equals log base pi of 4x plus 8. I do not like the way this feels. Let me do the first couple steps here, and then I'll set you loose to see if you can finish it up. Are all of the terms logs? Yes or no, but we have a log term here, we have another term here, and another term here. Yeah, they all seem to be log terms. Cool. Next step, condense. You must condense before you solve. Sorry about that, I had a bit of a relapse. Okay, so you have to condense. So let's do that. That means this left side will become log base pi of x plus 2 times x minus 2 equals log of 4x plus 8. So then we can set these two arguments equal to each other, and I'm going to go ahead and let y'all try solving this one. Again, I will release some steps as I go, and hopefully you all can understand everything going on here. Okay, here it is. We have x equal to 6. So what did we do here? Condense the logs, check. Set the arguments equal to each other, check. We have to distribute this left side to be x squared minus 4, check. We had to subtract 4x and 8 from both sides, so this would have been x squared minus 4x. Combine these two, minus 12 equals 0, check. Factor this expression, yep. Set each factor equal to 0 and check our answers. So what that means then is that we have a 6 that works. So 6 plus 2 is 8, that argument is positive. 6 minus 2 is 4, that argument is positive. 4 times 6 is 24, plus 8 is 32, that argument is positive. And this is the first example I get to show this. Normally, if you just check the first log, let's take negative 2 here. Negative 2 plus 2 is 0. 0 is not a positive number. So I know just from this first log that this answer will not work. It also will not work from this log. 4 times negative 2 is negative 8 plus 8 is 0. Even if your answer gives you a 0, that answer is no good. It must be a number bigger than 0, aka positive. So negative 2 does not work, and in fact negative 2 definitely doesn't work, and it's easier to see if you use it here. Negative 2 minus 2 more is negative 4. All right, one more example. It's going to be the same idea. I'm just going to flip over to the next slide. You try it, and I'll release some steps slowly. All right, there you have it. All these steps. So as a quick review, when I look at this equation from the beginning, not all terms are logs. Here we have a -2. There's no log in this term. So we have to move all the log terms to one side and all non-log terms to the other side. So that's what this portion was. I just rewrote the equation that was here and showed how you can do that. To get rid of a negative log, we add it to both sides. To get rid of a -2, we add it to both sides. So on the right side, we're left with a 2. And on the left side, we have this log plus this log. Then we have to condense these together, and when you add two logs together, that means we will use the product rule and multiply the two arguments here. Now that we have a log equal to a number, we can rewrite it in exponential form. The base is 4, the exponent is 2, the argument becomes the quote-unquote answer. That's why it's over here by itself. I squared 4 to get 16. I distributed the x here to get x squared minus 6x. I subtracted 16 from both sides, factored, set each factor equal to 0, checked my answers. -2 does not work. If you substitute it in for this x, it's log base 4 of -2. That's a negative argument. No good. 8 does work though. Log base 4 of 8, that's a positive argument. Negative log base 4 of 8 minus 6, 8 minus 6 is 2. That's a positive argument. So we are good to go. 8 is the answer. All right, as a very, very, very brief review, when you're solving exponential equations, you try to make similar bases to solve. And if you cannot make similar bases to solve, you want to isolate the exponential term and rewrite the equation in log form, solve for the variable, and then this is new, you want to use the change of base to get an approximate decimal answer, and we say go out to 4 decimal places, and we can clarify that a little bit more once we see some real world examples. But this last step is mostly used for when we start talking about finances, and we'll get to that in just a few minutes in this video. But here, just again, one example, I have 9 to the x plus 5 equals 27 to the 3x plus 11. Now, it might not look like it because in the process I gave you, I said you have to pick the smaller whole number base. In this case, it's 9. But I don't know what power of 9 will give me 27. The next step that you want to tackle is think to yourself, is there a base that is not listed here for 9 and 27 that I can turn a 9 and 27 into? Well, if you start thinking, you probably know that 9 is 3 squared. And so if you can rewrite this 9 as 3 squared, can you also rewrite this 27 as 3 to some power? And the answer is yes. So you have to look for even smaller bases if it doesn't immediately work. Look for a smaller base, see if you can do it. That'll make your life much easier. So here we can do this. So now look at this. We have base of 3 on both sides. From here, we can distribute the exponents. So 2 would get multiplied to the x plus 5, 3 would get multiplied to the 3x minus 11, and we would end up with an equation that looks something like this. 3 to the 2x plus 10 equals 3 to the 9x plus 33. Awesome. All right. From here, now that we have similar bases, we can set the exponents equal to each other. So 2x plus 10 equals 9x plus 33. I can subtract 2x, that'll cancel those out. I can subtract 33 to isolate my x's on the right side of this equation, minus 33. And what happens here? We get a negative 23 equals 7x. And sometimes the answers just get to be this odd. To solve for x, we divide by 7. There you go. X equals negative 27 over 3. I thought I had this example planned to go a different route, but it's always good to see weird answers just so that you don't freak out. Yes, negative 27 over 3, or 23 over 7, correct answer. Let's look at the next slide. We're going to be doing some matching just to really make sure you fully understand what you need to do in order to solve exponential and log equations. All right. We are dealing with money on this slide. These are the same two equations that you've been working with before, the compounded monthly or daily, or we'll say nthly, and the compounded continuously. Except now we will and can solve for p or t in this equation. And we could have solved for p earlier. I just never did an example like that. And for the continuously compounding equation, we can now solve and will solve for p, r, and t. Mostly because we have to get the variable out of the exponent. You can see t is in the exponent and r and t here are in the exponent. And we will have to use logs to get them out of the exponent. Let's look at some examples. How much money do you need to invest into an IRA? It's just an individual retirement account. To have $4 million in 35 years if the account yields 9% compounded monthly. All right, so we are going to set this up just like we have all of the other finance problems by listing all of the variables that we will have in our equation that you can see here. A equals p times 1 plus r over n to the nt power. And I knew it was going to be this one because I see monthly. The only time that it won't be this formula is if you see the word compounded continuously, or continuously compounded, or compounded, continuous compounding, something like that, with the word continuous or continuously in there. So here it is. We know that we want to have $4 million 35 years from now. This is a future amount, the accumulated amount to be $4 million. We need to find out how much money to invest right now. We do not know our present value. We do not know what we need to start with. But we do know an interest rate, which will become 0.09 as r, as a decimal, because we have to have a decimal to work properly with the formula. We know there will be 35 years and it will be compounded monthly. Now, off to the side here, I know I'm going to have to multiply t times n because it's in the exponent here. And when I do that, I get 420. So 420 will be in the exponent up there. And what else do we need? We need to divide r by n. And if we divide r by n, we get 0.09 divided by 12 is 0.0075. So I'm doing these little calculations that we were doing in our problems anyway, here and here, like we're doing them over here, and I'm just going to plink these numbers in the formula. So we will have AA is 4 million, there we go, 4,000,056 equals P times 1.0075 to the 420 power. Now you can sort of see what's going on here. We have P times some number equals 4 million. So if I can just figure out what this number is, I can divide both sides by this number here. And as it turns out, if you take 1.0075 to the 420 power, you get 23.063384, approximately. So if we divide both sides of this equation by 23.063384, that'll cancel with this, 23.063384, and we will get that the beginning amount that you would need to start with is a mere $173,435.09 if you round to the nearest cent. And I like exercises like this. And that, well, this is the answer. It's $173,435.09. That's what you need now to put into an account. Let it sit there for 35 years at 9% compounded monthly. The real world problem with this, though, is that this is not how savings normally work. If you want some more information on how savings work, I will try to get a new video up at some point. It involves something called an annuity, where you put some money in each month instead of trying to start out with some lump sum at the beginning and letting it ride for 35 years. Over those 35 years, you're saving a specific amount of money each month. Anyway, so yes, this is the answer here. All right, next, example 2. We have this question: how long will it take for your initial deposit to double or triple, we'll get to that too, if your money is in an account making 2.15%? And we'll take a look at 0.05% as well. So this is interesting for a multitude of reasons. We can assume, let's assume that since this is real world, we can say that this is compounded monthly. So we will be using this formula again. A equals P times 1 plus R over N to the NT power, which means I have to list out all of the variables like I did up here. So here are all the variables: A, P, R, T, and N. We know N is monthly, so N is 12. We're trying to figure out, here it is, how long. That's what we don't know. We don't know our time. Next, we know the interest rate is 2.15%, which really means it's 0.0215. If you move the decimal point 2 to the right, you can see we're at the same number as the percent here. And then this is really interesting. We don't know what we're ending with, and we don't know what we're starting with. We have A and P. What are those values? It just says your initial deposit to double. Well, don't we know that the initial deposit, we don't know what it is, but it's going to be, let's just call it 10,000. Double that will be 20,000. Okay, so there we go. And you can pick any numbers. You could pick 1,000 and 2,000. You can pick 50 and 100. You can pick 5 million to 10 million. It doesn't matter. Just pick 2 favorite numbers. It's perfect. So we can substitute all of these numbers in. The accumulated amount being 20,000. The principal being 10,000. 1 plus, what is it? 0.0215 over 12 to the 12t power. So this is our first instance where the variable we're looking for is in the exponent. And this is what we were getting to learning about the log equations and how do you get a variable out of the exponent. And it turns out we still want to do the same things. We want to simplify this r over n, which will be what you see here, 1.00179166 out to a bunch of decimal places to the 12t power. We can't simplify the exponent this time. And in order to solve for t, we need to isolate the exponential piece, the exponential factor. And for something to be an exponential piece or exponential factor, it needs to have a base and an exponent. So this is the exponential piece. There's the base, 1.001799166. There's the exponent or the power, 12t, which means this 10,000 we need to get rid of. So this 10,000, we're going to divide both sides by the 10,000. And you can see here we will end up with 2, right? 20,000 divided by 10,000 is 2, times 1.001799166 to the 12t power. So when you are working with these interest equations, the possibility of getting a like base ever is near impossible. So in order to solve this, we will have to rewrite this as a log equation. So let's take a look at how we can do that. We can take this this equation. We can say the log will have a base of this. Let's see. The log will have a base 1.001799166. So log of 1.001799166. There we go. It will equal the exponent, and the answer that was over here will become the argument. There we go. Now the only thing we have left to do here is solve for t, which would be to divide by 12. Divide by 12. And so what this tells us then is that t equals this expression right here. That is log base 1.001799166 of 2 divided by 12. And t represents years. So this is this many years. Which I'm going to just go ahead and assume if you walk up to somebody on the street and said, hey, you know what, you seem like a cool person. Let's meet here in log base of 2 over 12 years. They're going to look at you like you're crazy. They're not going to have any idea what you were talking about. You have to put it into terms people will understand. So this is where the change of base formula comes in. So if you take log of 2 and divide it by log of this base, you'll get a decimal number, which we then can divide by 12 and have it make some real sense. So if you do everything correctly, again, use the change of base formula on this log here, log of 2 over log of the base, get some number, divide that number by 12, you'll see that the time will take about 32.27 years for your money to double. And even better than that, if you decided to pick 2 different numbers for your starting and ending amount over here, let's just say you picked 100,000 and 200,000. If you put those values over here into this equation, if you made this 100,000 and this 200,000 and you ended up dividing 200,000 by 100,000, you would still get 2. The only pieces of information that you need to know in order to find out a doubling time or a tripling time or anything like this are the interest rate and the number of compoundings that will happen in a year. And that should just blow your mind. That should blow your mind. Guess what? If we were going to look at the tripling on this slide, and I'm not going to do it on this slide, I'll do it on the next one. We just changed this number to 3. This is where all the magic happens. We have a doubling 2 times. We have a tripling 3 times. Yeah, I mean, it's that easy. Let's take a look at that. If we want the money to triple, and we know we're going to have the 2.15% interest from the previous slide compounded monthly, how long will it take for the money to triple? Well, again, we have already done our dividing. So, for example, if we had 150,000 on this side and 50,000 on this side in our parentheses to the 12t power, we would have to isolate the exponential piece first. Again, we have to do it here, which means we would have to divide by 50,000. And when you divide 150,000 by 50,000, you'll get 3. So a tripling effect means we just have to worry about that set of parentheses and the exponent and set it equal to the amount that we are looking at, tripling or doubling or 10 times as much money. If we wanted 10 times as much money, we could just replace this with a 10. All right, but it's a very similar idea. We have to rewrite this in log form, which would be, again, log base 1.0017 9166 equals the exponent, and the answer, the 3 that we had, would become the argument. So now we can divide by 12 to solve for t, and I can actually write out on this slide what I did on the previous slide when I didn't have enough room. I took this top piece right here, this 3 log base blah 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 3, and I used the change of base formula 1.00179 There we go. And I got some number like 613.73, 613.73, 0376. Okay. But that's just the top part, remember. Then we have to come along and we have to divide that by 12. 613.730376 divided by 12 to get, does that drop everything everywhere? 51.14 years. 51.14 years. And that is how you can make sense of what logs look like. I'm going to leave that 0.05% example off this video. I wanted to do it because the 0.05% is quite literally an actual real world interest rate that you can get on your money. And for the sake of time, I just put it up here so you can see the time to double if your interest rate was 0.05% and you were compounding monthly would take almost 1,400 years. That would be like 16, 17, maybe 18 generations for your money to double. So you always want to find a better interest rate. It will shorten your doubling time. But the whole point here is that you can now solve for t in your nthly compounded interest equation. Let's take a look at continuous compounding and call it a day. Final example, what interest rate is needed for continuous compounding to make your money grow from $10,000 to $100,000 in 15 years? So here we go, key word, that word right there, continuous, continuous. Continuous tells you you'll be using this formula, the continuous compounding formula. So we are starting with $10,000, which feels a little more realistic, at least more realistic than the $173,000 we needed a couple examples ago. So $10,000, we're trying to grow it in the future, our ending amount, to $100,000. We have 15 years to do it. What interest rate do we need? Well, we can just plug all of our numbers in there. So 100,000, that would be 10,000 e to the rate we don't know times 15. And we can just rewrite that as 15r if you wanted. There we go. So 100,000 equals 10,000 e to the 15r power. We're trying to solve for r. Now, since again this is an exponential equation, we have to isolate the exponential piece before we do anything else. So this 10,000 that's being multiplied here, we need to divide by that. So let's divide both sides by 10,000 to get rid of that. 10,000. That leaves us with 10 equals e to the 15r. Now when we want to take this equation and write it in exponential form, log form, we know that the log will be e, or the base will be e, because that's the base of the exponential piece. We know that will be equal to 15r, because that is what the exponent is. And the answer we have here, again, will end up being the argument. Now this is so much better. I like this so much more because log of e, log base e, is just natural log. And with a natural log, we don't have to use a change of base because it is already one of the logs that's computed on most calculators. So if we just take log of 10 and divide by 15, we can get our interest rate. So the interest rate is log of 10, natural log of 10 divided by 15. And so that is 0.153506. Now, again, rates in the real world make more sense if it is a percent. Now, if you're going from a decimal back into a percent, we have to move the decimal point 2 to the right. So this would be 15.3506% interest rate. The process is almost identical if you're solving for a time. It's just you'd be having a t here instead of an r. All right, that concludes this lengthy video for solving all sorts of exponential and logarithmic equations and how we can use that to our advantage to answer more questions about money. Hope this makes sense. Good luck.